So the question is, why does a rock have as much energy as an atomic bomb, and how come this isn't our experience in everyday life? The answer is you cannot get at that energy under normal circumstances. It is inaccessible. Let's talk about why it exists. Well, okay, this is going to be a little bit of circular reasoning. Basically, it exists because, I'm being a little sarcastic, because Einstein said it would. And this is what I mean. Einstein came up with this equation for reasons other than experiment, just based on the physics that he was developing. Now, just leave that aside, okay? Leave that aside there. And actually, well, just leave that aside. Then let's look at what happens inside an atom. Let's say let's do the simplest type of fusion reaction, which is when you fuse two hydrogen nuclei. And you'll learn more about this when Cindy does elements with you and chemical reactions. You'll learn more about this, but you should all know from basic science that an atom is a proton, well, let's do it this way, a proton, P, a neutron, N, and an electron around the outside. For nuclear physics, we'll just ignore this electron, and we're just dealing with the nucleus. And in this case, we're not even going to worry about the neutron. We've just got protons. Okay? So let's say we have two protons, and we want to stick them together. What kind of forces are they going to experience? Anybody know? Michael, nice and loud.
They're going to want to push against each other.
Right, they're both positives. It's like trying to push two North Pole magnets, the North Pole of two magnets together, they're going to push away. So they're experiencing a force due to the electrical force that way. However, there is a much, much stronger force than the electrical force called the nuclear force. The nuclear force will act to pull them together. However, it only acts over extremely small distances, and so until you get those electrons very close to each other, you have to push them hard together. But then, when they reach a certain distance away from each other, so I've now pushed this proton right next to this one, and now the force due to the electric field, the electric repulsion is now enormous on them, but you're starting to see this nuclear attraction between them. And now let's zoom in and push them even closer together. Okay? Now they're getting almost right next to each other. You have a huge electric field or electric force, but you have an even bigger nuclear attraction between the two. And it's hundreds, if not thousands of times stronger than the electrical force that is attracting them. And so once you get them close enough, they on their own, they stick together. Okay? So on their own, they will stick together because of the nuclear force that is attracting them. So now we have our two protons stuck together, and there's a lot of electrical repulsion, but because they're so close, there's a great deal of nuclear attraction, and the nuclear force holds them together. So nuclear force holds atoms, or holds nuclei together. Now, here's the interesting part. Did you do work to put those together? Yes, you did, because you applied a force. Here's a force over a distance, and that's work. So you did work to push these protons together. Sorry, wait a minute. Okay, Force times distance equals work. Okay, so you did work to push this together. Now, in the process of doing work to put this thing together, oh man, this isn't working out. Okay, so you did some work to put these things together, but something crazy happens. Let's say that before the reaction, okay, it does work this way. Each proton, say, has a mass unit of 1 before you put them together. Well, after you put them together, what would you expect the total weight to be?
2.
2, correct. But Mother Nature fools us, and it's something like 1.98. Okay. This is called a mass defect, and I am not explaining why this happens, just telling you that it does. And the problem with this is that you lost some mass, right? People are always trying to lose mass. It's kind of a major preoccupation. But in this case, when you lose mass, it becomes energy. So that 0.02 is now going off into space as energy. And what we've just done is what's called a fusion reaction. It's one of the main types of nuclear reactions. Fission is when an atomic nucleus splits apart. Fusion is when they come together. And it's a very technical topic. We don't need to get into all of it. But basically, the point is we have this mass defect, and Einstein's equation tells us that the missing mass has become energy. Okay? Now, if you have to split these apart, you got to put that energy back in to get your hydrogen back from your helium. All right. So basically, this is why you can't. Here, just make a new sheet here. This is why you can't get at that energy that's in your 1 kilogram rock, 1 kg, is because you'd have to either fuse all of the atomic nuclei in there. I mean, you'd have to put so much energy in to get that energy out, and it's very difficult to do that. So fusion, for example, the only fusion reactions that humans have been able to do that produce more than you put in are what? Does anybody know? Yeah.
Uranium?
No, that's fission.
Exothermic?
No, okay, we're just going to get confused. Here we go. The only nuclear reactions that allow us to get this energy out are nuclear bombs, but it's not controllable. It just destroys things, and the energy all comes out at once. And the way they do it is they literally take a sphere of liquid hydrogen, and around it they put a sphere of plastic. Around it they put a sphere of uranium, and around that they put a sphere of plastic explosives. The plastic explosives blow up and cause the uranium to undergo fission. So this is a bomb within a bomb within a bomb, and it's all imploding. Okay, so the outside one implodes. It causes this one to implode So this is the type of bomb that we developed during World War II, the uranium bomb, which is a fission bomb. And then this one blows up, and it's just the igniter for the hydrogen in the middle. And then this one blows up, and that's the hydrogen bomb. That's the most powerful type that's a fusion bomb, is what that is.
But it's the uranium that makes it radioactive, right?
Well, there are a whole bunch. I don't want to get into all that, but there's a lot of radiation that happens from all the reactions. But anyway, this thing blows up, and let's say this thing weighed let's say it weighed 10 kilograms when you started. if you were able to reweigh the products of that reaction, it would then weigh 9 kilograms. Okay, so a whole kilogram went into pure energy, which in all kinds of ways. It went into heat, it went into sound, it went into kinetic energy all over the place, it went into tons of electromagnetic energy. So that this is the only type of process we humans have developed to liberate that energy defect, but it's not useful in the sense of anything positive. So, okay, that explains why you can't get at that energy on an everyday basis. You can only get to it under very special circumstances like this. Okay, that concludes our lecture for today. There will be online content for the relativity part of the class. We're not going to have time to get into that right now. And it's going to the illustrations will be far superior to the ones you are experiencing now. So have a very good morning, evening, or afternoon, depending on when you are watching this lecture. Goodbye.